Okay, welcome again. We can start when you dispose.
Yeah, do I introduce speakers afterwards?
Is Dalia going to?
Okay, very good.
Okay, let's go continues. It's a pleasure to me to present to next speaker, the Professor Garrett. I'm going to read something about him. Okay, the Professor Garrett Subspace obtained his PhD in mathematics from Arizona State University, Tempe, Arizona in 1971. His principal interest has been in developing William Kingdom Clifford geometric algebra as the geometric extension of the real and complex number system. He is co-author of the book Clifford Algebra to Geometric Calculus, a unified language from mathematics and physics, first published in 1984 after a 10 years editorial delay. He authored another book on the same theme, New Foundation in Mathematics, the Geometric Concepts of Number, published by Bierhaus Springer, 2030. He is co-author and co-author of numerous other books and articles published in international journals, such as Aim and Is Notice, the Mathematical Monthly, the College Mathematical Journal, and most recently in Contemporary Mathematics. His research interests include topics in mathematics and physics, such as multilinear and tensor algebra, differential geometric, numerical analysis, special and general relativity, quantum mechanics, and the teaching of this subject at the undergraduate and graduate levels. He has held postdoctoral research position at the Institute of Mathematics and Theoretical Physics at the University of Brooklyn, Poland, and teaching position at Arizona State University, Spring Hill College in Alabama, and Lander University in South Carolina. During 1991 to 1993, he was invited by Professor Jaime Keller to work on his new journal, Advancing Applied Clifford Algebra, and to teach at UNAM, Cuautitlán Izcalli, where he and his wife, Wanda, fell in love with Mexico. From 1993 to 2008, he was a professor of mathematics, and from 2009 to the present, professor emeritus at the Universidad de Las Américas Puebla. Sorry. Please, Professor, we ready to listen to you.
Well, thank you very much, Dalia, and I will, and thank you to the organizers. It's been an excellent conference, and my memory of all Zbyszek's conferences has also been my favorite conferences. So you're certainly continuing that tradition. So I will now share my screen. Let's see, how is this going to work? Okay. Okay, let's see. Okay, I gotta get out of this, I guess. Why is that? I'm getting an extra screen here that I don't want. What's wrong here? Okay, I see it coming up at least. Let's get this out of the way. Okay. Screen. I need to cancel that or I might get into trouble. Okay. Okay, let's see, I can reduce this thing. Okay, top here. Okay, so my talk is entitled Spheroidal Quaternions. And basically, they arise when studying a Laplace equation, a separation of the Laplace equation into three differential equations, second order differential equations. In particular, they're unusual quaternions in the sense I, j, and k like ordinary quaternions, but they're related in a special way to each other in such a way that d of the derivative of the I is equal to j, the derivative of j is equal to minus I, and the derivative of k is equal to 0. So we'll see how that works. So basically, I'm going to talk, I have 4 sections, just introduce some basic notations in geometric algebra of Euclidean space. And then I'll more formally introduce spheroidal quaternions, which arise from spheroidal coordinate, as you'll see, and how you construct harmonic polynomials using spheroidal coordinates. And then I'd like to talk about the relationship of Clifford geometric analysis, which is what we just called it geometric algebra and geometric analysis versus Clifford analysis. And of course, my talk is dedicated to the memory of Zbyszek Ojevich, who I've known for, 40 years probably. So I'll start with this picture here. This was taken in the year 1991 in Scranton, Pennsylvania, during the first Iraq war that the United States started bombing Iraq, as everyone knows. And then, of course, the follow-up is what we're experiencing, 20 years ago. So this, and of course, also was involved with Zbyszek in Wrocław, Poland during the revolution that took place in Poland. In fact, I was jailed along with Zbyszek for distributing pamphlets regarding fighting solidarity. A lot of information I have on my web under fighting solidarity. which other speakers have talked about already. So this picture is also taken in Scranton, Pennsylvania, about 1991. This is where Zbyszek told me about the conference that was going to be held in New York. And it was at this conference that I met with Professor Jaime Keller, and he invited me to Mexico. So it was to Zbyszek. Zbyszek has not only at the University of Wrocław, where I got to know Zbyszek, but major decisions of my life have really followed from my interaction with Zbyszek, not only scientifically, but on a personal level. So, okay, so the history of my subject, what I call it's hard analysis. It's really quite new to me, and in particular, in this particular talk, I've been very interested in Laplace's equation and the Helmholtz equation and solutions of these equations using separation of variables methods in spheroidal coordinates, as I'll talk about. So it's really has extremely long history, dating back to 1842, Lamé, Newman in 1851, and Heine. Well, Heine, I met as a graduate student with the Heine-Borel theorems. It's the same Heine. So, well, more recently, Hobson in 1939 and Garabedian in 1953. A very important reference for this, my particular work I'm going to be talking about today is William Miller Jr., who wrote some revolutionary papers, I think, in 1974, developing these older ideas and understanding the relationship between symmetries and solutions of Laplace equation and the other 11 coordinate systems in which the Laplace equation, you're able to separate variables. So this is what I'm going to be talking about, is separation of variables in spheroidal coordinates. Okay, so there are two types of spheroidal coordinates, namely prolate and oblate. As an example, the Earth is an oblate spheroid, whereas an American football is a prolate spheroid. I'll have a picture in a minute. So Laplace and Helmholtz differential equations are separable in spheroidal coordinates, extremely important. And harmonic prolate and oblate Legendre P and Q polynomials, which are used in the solutions of the Laplace equation. Well, here's just a slide demonstrating the Legendre polynomials of the first and second times, whether the generalized Legendre polynomials, they call it associated Legendre polynomials. So they're very well known, but of course they date back a couple of hundred years. So particular, I'll be interested in using these polynomials. I've done calculations in Mathematica. I would never even approach these problems without being able to do calculations on Mathematica, because I don't see how these earlier mathematicians could possibly get through this material without serious calculations that are involved, or just you make one mistake and you go off on long tangents that even with Mathematica, you make one mistake and you get page after page of printout or on the screen. Okay, so my first section, as I emphasize in the review, I'm mostly interested in geometric algebra versus Clifford algebra. Well, I make the distinction, geometric algebra is actually, I consider geometric algebra to be the extension of the real number system to include unit vectors which have positive signature or unit vectors which have negative signature. But in the Euclidean space, geometric algebra Euclidean space, it's natural to pick out, well, usually it's the X, Y, Z axis, but instead I'm going to be using X0 for the Z axis, where E0 for the z-axis and E1 and E2 for the x and y-axis. And of course, so you're extending the real number system with 3 anti-commuting square roots of +1. Well, of course, normally complex numbers is built up by extending the real number system by a square root of -1, called, usually identified as imaginary numbers. But geometric algebra G3 has much more interesting structure, which I can't believe after 50 years now of working on this, it's still not taught at a low level. It's just, for me, it's almost a slap in my face that for 50 years I've been working on this, and still people insist upon only using Gibbs Heaviside vector algebra. Well, it is simpler, but it really fits into very nicely, and it makes it far more powerful if you embed it in G3 and properly identify vectors and bivectors as being, well, again, dual to one another, but not in the sense of covectors, a topic I've discussed with Zbyszek on numerous occasions that we never could quite agree with it. Okay, so we have, I'm just using x and y for coordinate vectors, x0, x1, and x2, and with respect to the E0, E1, and E2, and then y, the second set of Euclidean coordinates using the same, just different coordinates, x0, y0, x0, x1, and x2, y0, y1, and y2. So the geometric algebra itself is an 8-dimensional algebra over the real numbers, consisting of a unit, 1, ordinary real number, unit, 3 unit vectors along x, y, z axis. Then we have 3 bivectors, which are their duals, can be identified with covectors, but I prefer a bivector. It's just like a directed line segment. A bivector is a directed plane segment. So again, bivectors are spanned by a set of 3 bivectors, which are dual in the sense that if you multiply, okay, by the unit trivector, 0, 1, 2, which is in the center of the geometric algebra, you get 0, 1, 1, 2. So you're distinguishing unit bivectors in Euclidean space have signature -1. So I noticed in a previous talk identifying covectors with waves and vectors with particles. Well, in a certain sense, you could try translating that into the geometric algebra, where waves would be identified with, well, the plane of the wave, which are bivectors, and rather than necessarily with covectors as in standard quantum mechanics. So again, I is identified with the unit trivector in Euclidean space, which, if you carry out multiplication, has square -1. So the imaginary unit for in our context will always be identified with a geometric object, namely the unit trivector or volume element, if you like. So of course, the geometric product decomposes into a symmetric part and an antisymmetric part, which we identify with the inner product and with the outer product, x, or the Grossman product, x wedge y. Okay, and now I'm going to introduce this special quantity, EP, which is where I'm getting the label for the quaternions, as just unit vectors in the xy plane, E1 cosine phi, E2 sine phi. And xp then is just the square root of x1 squared plus x2 squared. And x then is equal to x0 E0 plus xp EP. Okay, so here is a picture of Zbyszek with my wife and I in South Carolina in 1992. So this was when I was working at Greenwood, in Greenwood, South Carolina, at Lander University. And this was a little, I had a little piece of land and took Spishig out with my brother to visit this piece of land in Greenwood, South Carolina, which I no longer have, but it was a nice retreat in the country. And I was taking Spishig around South Carolina a little bit. Okay, so spheroidal, what is a spheroidal quaternion? So we introduce 3 bivectors as in standard quaternions, but we define IP equal to EP times E0. So remember, EP is just the unit vector in the XY plane, which we identify with the coordinate at the angle phi. JP is a derivative of IP because we're just taking the perpendicular vector to EP in the XY plane. And K is a product of IP and JP, and it's equal to, when you multiply it out using the rules of geometric algebra, you just get EP dot, which is the derivative with respect to phi, times EP. And okay, and then if you look at the rules then, well, here it is. Okay, remember EP dot is minus sine phi, E1, E2 cosine phi. Okay, and the rules are exactly the same as ordinary quaternions. I squared J squared equals K squared equals -1. IP times JP is equal to KP. JP, KP is equal to IP. IP times JP times KP is equal to -1. But then we have these extra relationships, which I'm denoting by dot. D of IP with respect to phi is equal to JP minus IP, and this is a constant then. So whereas Hobson and these classical writers introduce only complex numbers, we instead introduce these what I call spheroidal quaternions because of their relationship to spheroidal coordinates. Okay, so now one reason for introducing these spheroidal coordinates is because the trig identities become unmanageable. They're just, just all over the place. But if you reduce it, if you define Z equal to eta plus IP theta, for the other two, eta, theta, and phi are the 3 spheroidal coordinates, then you can simply express these things, and you don't need to always have these trig identities popping up everywhere then. So if I take the derivative of Z with respect to eta, then all I'm really doing is changing, or here it is. You're just changing cosh into sinh, but the cosine and the sine remain the same. Okay, here we have, so then my spheroidal coordinates are introduced in terms of these spheroidal quaternions by mu is just a constant. You can relate that to an ellipsoid and the standard definition of an ellipse and ellipsoid. Okay, so X then is mu times E0 cosh eta cosine theta, EP sinh eta sine theta. So this introduces spheroidal coordinates in terms of eta, theta, and phi. So that's spheroidal oblate spheroidal coordinates. And the prolate is, well, you can see the relationship. I'm using X then, position vector X to relate to a prolate spheroid, and oblate is just the derivative of Z with respect to eta, well, times E0. That changes into a vector, E0 and EP, and the okay, and the Y then is the corresponding, but just differentiating the Z. So there's a direct relationship between prolate coordinates and oblate coordinates simply by taking the derivative. Well, here I express it as y is just equal to the derivative of the position vector. So the position vector in the oblate spheroid is just the derivative with respect to eta of the prolate spheroid. Okay, so here I'm going to show you a figure relating, if you take a constant eta, which I choose to be equal to 2/5, then and take z and divide it by just cosh 2/5, I get cosine theta plus IP, which is now considered to be a function of eta, times 2/5 sine theta. And if you graph that, well, here you have it. This spheroid here is the prolate spheroid, and the oblate spheroid is a y coordinate then, well, position vector. So each position vector x is on the bounding spheroid, which you see here, the prolate spheroid, and the bounding spheroid for the oblate case is this oblate spheroid, the bounding spheroid. So I divide zeta n by cosh 2/5, and I get the coordinate equation of the bounding spheroid. Okay, now if you look at just simply tangent of eta plus IP theta, you get, that's the same thing as z derivative with respect to eta times z inverse, which is a nice expression rather than expressing everything in terms of eta, theta, and phi, expressing in terms of the coordinate, the spheroidal quaternions. Okay, so here I'm relating the two coordinate systems by taking the geometric product of y with x inverse. So you can see what the relationships, very simple relationships between the derivative of eta of z with respect to eta and z inverse. Okay, so now note that we can write y just a simple geometric algebra identity. Y is equal to y times x inverse times x. So now we decompose y inverse y times x inverse in terms of a magnitude. The magnitude of the vector y times the magnitude of the inverse vector x, and then it's times a rotation e to the rotation in the plane of IP times omega, some angle times x, where cosine omega is just equal to y hat, the unit vector in the y direction, times the unit vector in the x direction. So you can make a transition from a prolate point, which is x in terms of the spheroidal coordinates eta, theta, and phi, to the oblate corresponding point in the oblate spheroid, spheroidal coordinates, eta, theta, and the same eta, theta, and phi is in the x, but it's just a different point on the prolate and oblate spheroid. So it defines a natural mapping between the oblate and the prolate spheroid for each value of eta. So I've chosen for the picture eta equal to 2/5, but eta could be any, or infinite many others. I suppose it would be interesting to look at that from Zbyszek's point of view of you could have a whole envelope of these prolate and oblate as layers of the other talks that people were talking about as relating Zbyszek's ideas. Okay, so we have a dilation then. We're decomposing x inverse times y. Okay, so it decomposes into a dilation, the magnitude of y times the magnitude of x inverse, and a rotation in the plane of IP, which is just the plane of EP times theta. Of course, in Hobson and these other classical writers, they use the same I for IP and for any other, they don't identify it as a bivector. Well, this is, you identify immediately as a plane of rotation relating these two spheroids. And well, the oblate and the prolate spheroid are directly related, which is, I think, very important. Okay, so we can actually calculate these quantities in terms of the spheroidal coordinates. You find that this quantity, in terms of the spheroidal quaternions, is z eta, partial derivative of z with respect to eta divided by z, which if you wanted in terms of the theta, and you can solve, basically these calculations are going with Mathematica, you get the relationship in terms of hyperbolic sines and cosines. So again, geometric algebra puts sines and trigonometric functions on an equal level, which was a basic idea of my paper for the College Mathematics Journal, as well as there I talked about the hyperbolic number plane, whereas I taught in that paper I was comparing complex numbers with hyperbolic numbers. And for the Mathematical Monthly, I talked more about these other relationships. Okay, so if you calculate then x hat dot y hat, you get this formula, cosine omega, and the bivector then is expressed in terms of IP times sine omega. Well, you can see that if you take the square and add these together, you get 1, as you have to. Sine squared plus cosine is equal to 1. Well, you have to change the sign there for that. Okay, you can calculate differentials in terms of, compare this with calculations, for example, that were given in Hobson, a reference set of this paper. For the differential squared of the lengths of the tangent differential to the spheroids. Okay, so this graph here is just a graphing of the angles between the position vectors to the bounding spheroid, prolate spheroid, and bounding oblate spheroid. And what you can see is that the angle generally is a right angle, well, almost approximates 0 and 1. So that's for when theta is equal to 0, cosine 0 is 1, or pi over 2, pi rather, it's -1, and cosine 0 is 1. And you can see the angle, the relationship between the tangent vector and the position vector. The tangent vector of the prolate spheroid corresponds exactly to the oblate spheroid, which is interesting. And again, this is for eta equal to any constant larger than 0. You can get easy graphs of these things with Mathematica. Okay, so this is a picture of when I arrived in, I was at FES Qualtitlan in about 1992, when Professor Keller invited me to UNAM to work on his new journal on advances in applied Clifford algebra. So the first job that, in addition to editing or helping with the journal, was to help invite Zbyszek to Mexico as well. The first few months, Zbyszek, in fact, we were living together in Qualtitlan Izcalli. So this is a picture of colleagues at FESC, and with my wife, and of course Zbyszek also new at FESC as I was. So I stayed at FESC for 2 years before maybe going to Universidad de las Americas, where I was invited to give a talk. we both, my wife and I, fell in love with the Universidad de las Americas in Puebla, a beautiful town as well. But unfortunately, I kept working on the journal with for quite a number of years afterwards, but we did relocate to Universidad de las Americas, where I stayed for the following 15 years, but maintained close contact with all my new colleagues at FESC, and of course with Professor Keller. So I was around 1992. Okay, and here is a picture in, this picture was taken in Wrocław, Poland, the Clifford Algebra Conference that was already mentioned by some previous speakers in Subotica, Poland, organized by Zbyszek, one of his many conferences that he organized, this one in Poland. And this is Professor Halprin, who was a Dirac's assistant at Florida State University for a number of years. And of course, Jaime Keller, Professor Keller. These are the daughters of Zbyszek. This is Ustina, and this is Amilka. And of course, my wife. A very, very beautiful conference in Subotica, and this was in Zbyszek's house. Zbyszek is really in this picture because he took the picture, so he was certainly in the picture as well. Okay, so I'd like to talk now about spheroidal functions, harmonic functions. So again, the associated Legendre polynomials are denoted by P and M of X, which is related to this other notation, n, x, by a minus sign, as well as the Q's. The Q's relate to areas outside the bounding spheroid, whereas the P are more used for interior to the spheroids. And they satisfy the second order differential equation, which is why they're which is where the Legendre polynomials come from, which is 1 minus x squared d squared dx squared minus 2x times n plus 1 minus m squared over 1 minus x squared. These coefficients are called connecting coefficients. When you actually solve these equations, they arrive. And I still, that was a puzzling to me, because I actually separated these equations myself and I got a related solution, but it wasn't clear how it was related. So again, looking at Hobson and some of these other references, unfortunately in Hobson, there are several typos or misprints, which can be very disconcerting, because it completely throws off calculations when you're actually trying to check these things with Mathematica. So what I did, I used the original Laplacian, the second order Legendre polynomials, solutions of this differential equation. And I mapped back using inverse functions to try to find out exactly why I was getting a different separation of coordinates than the usual one that are given with these constants of connection, n times n plus 1 and m squared, m and m squared then, which are the classical solutions. So I inverted these to get back to x from the spheroidal coordinates then. And it's just calculus. Using the inverse functions, we calculate that eta is equal to cosh inverse of x, and d eta dx, when you map it back, is 1 over sinh eta. And the second derivative, well, you go through these calculations just using the inverse functions, and you get it back to, so I want to relate this differential equation in eta to the corresponding second order Legendre equation in X. And these are the formulas that you need to do that. And when you do that, you get the separated variables in terms of eta, in terms of exactly the Legendre equation. Okay. And similarly, okay, so we separate into 3 variables, eta, theta, and phi, and you get these differential equations, which of course is the Legendre differential equation using the Legendre classical solution then. And of course we have the, so when I separated the equation, my separation of variables led to n times n plus, wait a minute, let's see. Okay, so this is the classical solution that you get. But now when I separate the equation myself, okay, in my recent paper 2021, I got a different set of differential equations. Laplacian gives these 3 equations. Well, my connecting coefficients now are n and minus m squared, and n plus m squared cotangent theta. So for me, I wasn't sure whether I made some mistake. And if you try solving these with Mathematica, you can't even get a solution with the standard classical solution. But when you translate it back, then you get the classical solution. So it became very confusing. In fact, even in this paper, I was not sure whether I had made a mistake or what the problem was. So this talk, I hope, is clarifying the issues in the paper that also goes with this talk. I hope clarifies exactly what the situation is, and that I'll come to in the next part of my talk here. Okay, so again, this is just separation of variables here into a function entirely dependent upon eta. A prolate solution. Okay, separation of variables into 3 functions in terms of eta, theta, and phi. Okay, so again, I'm using this reverse engineering. I'm going back to X to make sure that there's no mistake in order to try to understand what the difference between my separated solutions are and the classical ones that people use, involving n plus 1, n times n plus 1, and m squared. So solving this equation, my equation, this is my differential equations, gives well, this solution right here, which is, well, closely related, but n prime is very complicated here. So again, what is the relationship between the classical n and n prime here? And what I found is if I just, okay, so this is a solution here that's given by Mathematica, where n prime is equal to this, instead of just n and m, as in the classical solution, I have these equations. Okay, but if we just solve this equation for n, I get m squared minus m bar times n bar plus 1. Okay, so how is that related to the classical solution? So why, how? Okay, so this is what led me then to start studying these symmetries of the Laplace equation, in particular for spheroidal coordinates. So following Miller's ideas that I referenced earlier, a symmetry of the Laplace equation is simply in terms of the gradient operator, which is a classical gradient operator in vector analysis. Take a unit vector, or take a vector and dot it with that. It's like a directional derivative, and you add to that a second vector cross the position vector in well, in this case, the prolate case that I'm using, the prolate coordinates. Then you dot it with x. Okay, so again, Laplace equation is giving solutions for a scalar, a real number valued function, which I call u of x. Okay, for analytic u of x, the analytic vectors a and b provided. Okay, so a symmetry then of the Laplace equation is all operators of this form. A symmetry of the Laplace equation, del squared equal to 0, is any symmetry of this form SAB, which, when composed with a solution of the harmonic Laplace equation, is also a solution. So if I multiply SAB times U, it still satisfies the Laplace's equation. So that's called a symmetry. So that is why I was interested in Hannah's lecture about symmetries of non-linear differential equations, because Laplace equation and the Helmholtz equation are linear second order differential equations. Okay, well, so what this paper of Miller says is that for each of the 11 coordinate systems for which you can separate variables, there are two important symmetry operators involved, which you can write now in geometric algebra as J0 as x cross E0 dot the gradient operator. Well, that's of course a scalar, because the cross product, this is the ordinary cross product of vector analysis. The algebra is put together very well, and that gives you a scalar operator, which I called J0. And then you also have the second operator, which is the dual, namely multiplying by the pseudoscalar or trivector of the algebra, we get the dual, which is, well, again, the outer product is closely related to the cross product in vector analysis, and it's just x wedge del x is equal to I times x cross del x. Okay, so that's where you get the minus sign from, because you're pulling out an I from taking the dual of this, you get minus x cross that. Okay, so J now is a symmetry operator. And now, which is very interesting, is to show that, well, first of all, if you take J0 squared, it's a kind of just an ordinary vector analysis identity. You can remember now, this is an operator rather than just because it involves, when you take the square, you have to differentiate this x at the same time. So what I want to show now is that J squared is very interesting. And if you take this operator and you square it, it's really can't be expressed directly in terms of ordinary vector analysis. You need the geometric product. Of course, x times del is x dot del and x wedge del. And of course, so I'm going to prove this, because this identity, I probably spent, I don't know how many pages, false attempts to really find the proper way of proving this. But once you get this identity here, you can show that J has these very interesting properties. Well, of course, it's just a vector operator. So it's dot and wedge. But you can express the wedge then as minus I times J. Well, that's interesting, because J squared is related. You can find a kind of a characteristic equation. J squared plus I times J minus J dot J is equal to 0. That's kind of like a a Cayley-Hamilton theorem for ordinary linear operators. Well, here you have some other very interesting identities, which are hidden in the standard approaches, which I think are very interesting. And I'm going to give you a proof because it's so simple, even though it took me, I don't know, 20 pages of calculations to actually, I'm not going to try to go through the steps of this, but I just might mention that in doing this, this dot here means that this gradient operator only differentiates x, whereas this one differentiates to the whole thing. So in separating this, you have to go through the details, but it's certainly non-trivial to find this. At least it was non-trivial for me to find it. Okay, so that's why I'm making this comment. Proof of this identity reminds me of my own proof of the Cayley-Hamilton theorem, which inspired me to develop geometric algebra. The ideas of multilinear, in geometric algebra, the ideas of multilinear algebra, my PhD thesis 50 years ago. So it seems like I'm now back to the Cayley-Hamilton theorem, but using symmetry operators, which is, for me, I've spent now the year studying this material, and I became very interested now in these symmetry operators. So the result of Miller then is whenever u is equal to just a real valued function satisfies Laplace equation, there exists two commuting second order symmetries, L plus and minus, which we can write as j dot j plus u squared times E0 dot del. And this one, L0 is equal to J0 squared, such that L plus minus this is equal to the connecting coefficients. That's the n and n plus 1 in this case. And forget the sign there, it's not important. Again, it's a matter of notation. And L0ux gives you, so these are the connecting coefficients. So that explains more how my connecting coefficients are related. Well, it should be just a translation and a rotation. I haven't really found that yet, but I'm also interested in Zbyszek's idea, or as Professor Page talked about, this third in his groupoid special relativity, how this third vector arises, which gives you the standard. So let me go on because okay, just a little history. So I give here a couple of examples which you can see in the talk. I'm not going to do it, but expressing exactly these connecting coefficients because I want to have a minute to so again, this L plus gives you, it's like an eigenvector or eigen minus, this is the connecting coefficient for n times n plus 1, where, okay, so that's 4 times 5 is 20. So that's where that number is coming from. And then this one is m squared. Well, m is equal to 2. So n is equal to 4, gives you 4 times 5 is 20. And okay, so I wanted to just say a word about Clifford analysis and monogenic functions. I think the two areas Clifford analysis, there's just the choice of the word Clifford analysis should be done in terms of geometric, what I call geometric analysis, because you can identify bivectors in quaternion analysis is simply, well, with bivectors in the geometric analysis, it becomes much more powerful. So again, I refer you to my paper in Contemporary Mathematics published in just this year, actually. Okay, geometric developed by William Kingdon Clifford. So geometric analysis, in our group of people, we developed Clifford's geometric algebra from the ground up. Well, some people say it's old wine in new bottles. Well, in fact, that's been a problem because in a sense, that's what we are doing. We are translating, putting old wine, very great old wine into new bottles, but I believe that is also very important. So reformulating basic concepts in mathematics and physics, and of course, that's what David Hestenes and many other physicists are doing with geometric algebra. The Cambridge group is very notable with Anthony Lazenby and Chris Dorn and Stephen Gull. Okay, well, geometric algebra has been picked up by the computer science and engineering computer, geometric. So the question is it possible to unify the two communities for the benefit of both? Well, I believe that G3 of Euclidean space, the extension of the real number system to include these bivectors, and that should be taught at undergraduate and even in high school. Okay, I'm just comparing vectors with power vectors and showing how it translates and how it really belongs in the same language. So again, I know I've run out of time. I'd like to leave a little time for questions. So this is in G3, symmetric. It's much more natural, I think, than trying to express it in terms of Clifford analysis, where you have, you have to take the conjugate. These are notations from Clifford analysis. So I'm okay. Okay, I just wanted to say about this, some formula again, but so that what Clifford analysis uses is this splitting of a vector with respect to E0, and then you have the way to translate from one to the other is that you certainly simply the usual standard sandwich in with E0, and you get the formula in Clifford analysis, a very simple relationship. But I also like to point out the splitting of the Pauli algebra into the Dirac algebra, which was extremely important in Hestides as a formulation of space-time and special relativity, along with the work of Chris Doran. I say then how the Pauli algebra is related to the Dirac algebra by splitting with respect to E0. The vector derivative here and in Clifford analysis, and how it's related to the standard gradient operator in Clifford analysis. So that's thank you very much for having patience with my talk. So are there any questions?
Okay, thank you very much, Professor Garrett. Okay, Professor Kosik is trying to make a question. Please go ahead.
No se escucha.
Yeah, your volume is your microphone is off.
I'm now unmuted. No, I didn't raise my hand, but I can still ask Garrett some questions. First of all, at the very beginning, you introduced hyperbolic trigonometric functions. So it would suggest that you're dealing with actually a Clifford algebra or geometric algebra, as you prefer to call it, for the space of different signature, not plus plus plus, but plus plus minus, right? But this is not the case, I understand. You are just using these hyperbolic functions as your parameters for the interesting shapes in the regular space. I think I'm right?
Well, the hyperbolic number plane I consider is really they're all subsets of the geometric algebra of G3, because any unit vector has square plus 1, and my hyperbolic number plane is the real numbers plus a unit that has square plus 1, which is not, of course, plus or minus 1. It's an extension of the real number system to include a unit vector,
okay,
or anti-commuting unit vectors for G3, for example. So as I say, I like to distinguish. I think the Clifford analysis people, because they're really just, again, rushing to get new results, they're completely just integrating it in with well, like people in Clifford analysis, they mix the two languages, just embedding, taking Clifford algebra, but not really being faithful to the geometric interpretations as bivectors and trivectors. It's not important to them. So for geometric algebra, the geometric interpretation is always very important. And of course, duality now is not just covectors in vectors, it's taking the dual with respect to the, in the case of G3, I, which is a unit volume element, which has square minus 1 as well. So it's a, it causes confusion, but I think it's an important distinction to make.
Yeah, right. Okay, thank you.
Okay, thank you. I think we have time for more questions.
Hannah,
Okay, Anna, please.
So just a quick comment. I also like to use Mathematica very much for symbolic calculations. It's a powerful, very powerful language. And because you asked me before if the method of symmetries can be applied to your equations, in principle, yeah. In principle, yes. And I even can propose that if you have a question like, are those two solutions equivalent or not? The first thing that may be checked is, do they possess the same symmetry? If they possess different symmetries, they don't have chance to be equivalent. But if they possess the same symmetry, it means that probably, at least in some sense, in this real algebraic sense, they are equivalent.
Well, yes, I think that's exactly exactly what Miller is pointing out in his paper. There's only 11 coordinate systems where the Laplace equation separates, and each such coordinate system has a pair of second order symmetry operators which commute. Somehow that distinguishes those coordinate systems. So I refer you to his paper, a very, very deep paper, I believe. I've learned a lot from that paper. And of course, that's how why I ask you a question about the relationship to non-linear differential equations.
So yes, I mean, the fact that I didn't study this means anything. It doesn't mean that it is not applicable. It is probably the same or very similar method. Thank you.
Okay, thank you. There is one more question, Professor Page.
Oh, yes. I wanted to, you mentioned that you are giving advice to teaching this subject in perhaps even in high school. And I wondered to what extent you can take advantage of the availability of tools like Mathematica to people at the high school level. Is this something that is possible, or is it something that's necessary in order to be able to teach this subject at that level?
Well, I think this geometric algebra of Euclidean space really fits in very well. You can even start by teaching, just a cross product is fine, but it should be related directly to the bivector. Of course, that's a different expression of duality, which I've argued with Spishik about covectors and vectors. Okay, yeah, I know. But it's a different concept of duality, which can be confusing to people.
Well, what I was thinking about it in particular was the intuitions that are necessary to develop in younger people to be able to take advantage of these more abstract concepts.
Well, I think when you introduce a directed line segment, the next idea, of course, is a directed plane segment, which of course arises in Grossman algebra. And well, Grossman himself was a high school teacher. I've taught it to my students, undergraduate students at Universidad de las Americas for many years, and also applied it to other applications, numerical analysis and so on, group theory. I've taught it in many different classes.
So you don't feel that teaching this would necessarily require more advanced tools, computers?
Well, no, I think you can teach it geometrically. A bivector is a plane segment, just a number which represents a plane segment. And you can draw planes and intersection of planes and immediately write down the correspondence. Now, as far as calculations, they do become more clumsy because we give up the commutative law. But that's true for ordinary vector analysis too. So, you have to do it gradually. But calculations become unwieldy, and that's why, of course, I use Mathematica.
Okay, thank you.
I suppose all of science now is becoming more hand calculations that are almost impossible now. I'm sure with a lot of people are doing now. Everyone's using computer calculations now.
No, I agree completely. Thank you.
Okay, then, thank you very much. And I think that we need to go to the next speaker. Professor Garrett, you are going to take
Perdón. Es que hay una pregunta de Bert Meikan. Entonces,
okay.
Yo creo que si le podemos abrir el micrófono, por favor.
Yes, open this. Okay.
A ver, ahorita.
Am I going to introduce Eckhart, Professor Hitzer now?
Okay, please.
No, que la pregunta de Michael, ¿no?
No, él está indicando que la puede escribir. Entonces vamos a continuar. Gracias.
Okay.
Okay, so I would like to say I've known Eckhart, Professor Hitler for...
Do you hear me, or what's the matter?
I hear you. Can you hear me?
Yes, I can hear you, Garrett. Hello.
Okay,
yes,
so I'm very nice to see you.
Yes, it's very nice to see you. Thank you.
Of course, we met in China. I don't know how many years ago, 2004. But,
yes, we met many times, I guess.
Most recently,
in the
I guess, in China.
institute in Vienna, you showed this beautiful picture of Ludwig Halpan. Yeah? Do you hear me?
Yes. Of what did I show you a picture of?
A group photo with Ludwig Halpan. Halpan was
yes,
well known. Yes.
Of course.
Halpan was very well known in Vienna in the high energy group.
Oh yes.
Rayleigh Theorem. And
yes.
I remember a writing by Halpan. Maybe you know it. It is by Halpan and Laurent on the gravitational radiation of microscopic systems. That was published in Nuovo Cimento 33 in 1964. I came, you know my work about the space-time spinors, and it is a little bit related to your own work. My question that arose from this working is simply, how do you see the duality or the relation between non-commutative algebra and commutative algebra within a geometric algebra?
I can't say I really can't answer your question. I think it's a very interesting.
Do you see the question as important, or don't you see it?
Okay, you're asking how. Maybe ask it one more time.
Okay, let's ask it later. Let's go over to Hitzer.
Okay, yeah, let me introduce you. You're speaking about a special affine quaternion domain Fourier transformations. Of course, that's been an important topic for expressing in geometric and Clifford analysis, as well as in geometric algebra. So go ahead, please.
Who should go ahead?
Yeah. So, oh yes, yeah. Let's go ahead. I of course know Brent.
Let's go ahead.
But we'll communicate as a note. So go ahead, Eckhart. So I would like to go ahead. I will write to Bernd Schmeckel.
It's okay. It's okay.
So
go ahead.
Hitzer, you have to turn on your microphone. We don't hear you.
Sorry, thank you.
Okay.
So we have the mic now. Can you see my presentation screen?
Yes.
Okay, yeah, that was what I was asking without a mic. Okay, I will now go to full screen mode. And so I talk about special affine quaternion domain Fourier transforms. Myself, I'm a Christian physics.
Can you move the windows that are over your presentation? Yes.
No, what is that? I mean, maybe it can minimize.
Okay,
Is this better now?
Okay. Mm-hmm.
Okay. So I'm a just continue. If there's anything, just interrupt me. I'm a Christian, a physics teacher, and a sort of, let me say, volunteer mathematician. And since about 9 years, I work at International Christian University in Tokyo, in Japan. And it's my honor to be able to give a presentation at this conference, in particular, the session on Clifford algebra and spheroidal quaternions. So at the beginning, I like to just make a brief quotation from the Bible, from King David, from a psalm. What is man that you are mindful of him, and the Son of Man that you visit? Or other expressions for this word are give attention to care for him. For you have made him a little lower than the angels, and you have crowned him with glory and honor. So I also thank my family, and I thank the organizers for inviting me. And please pay attention that this presentation is delivered under the terms of the Creative Peace license. You can see the details here. And I make a special dedication of this talk to Dr. Judy Mikovits. And why? For example, if you read her recent book, Plague of Corruption, Restoring Faith in the Promise of Science, you'd understand. And I know that Professor Ostrovich, he has been very courageous, not only to challenge scientific problems, but also to help bring the politics of his country into the right direction at personal risk. And I think somebody with the same kind of mindset is Dr. Judy Mikovits as well. Okay, I'll proceed by giving you a brief introduction, then background on quaternion algebra, which actually Garrett has done well for me already, but okay, I'll just review it. And then I talk about the special affine quaternion domain Fourier transform. I define them, show some properties and the uncertainty principles and the conclusion. So, oh yeah, this is a bit in the way. I'll put that here. Okay. So in signal processing and optics, these special affine Fourier transforms were introduced by Sheridan and Abe in 1994, and they greatly generalized Fourier transform, fractional Fourier transforms, and linear canonical transforms, so all unifying them under one transform with several parameters. Then in recent decades, hypercomplex transforms, that is Quaternion and Clifford, or we could also call them geometric algebra Fourier transforms, have been introduced. And in particular, I've proposed the quaternion domain Fourier transform on signals defined on the 4D quaternionic domain. And also these signals have range in the quaternions. Now, for sure, the quaternions can always be understood as the even subalgebra of the geometric algebra of three-dimensional Euclidean space. And all this would also work in this framework. Applications are potentially for electromagnetic waves, light, any area of physics, electromagnetism, especially satellite navigation, optics, quantum mechanics, space-time, crystallography, very recent new subject, and interest to quantum bit computations and quantum computing. Now, before Garrett's talk, I only had Stirrup's bit of quaternions as something interesting in this context as well, but since his presentation, I just added these few formulas to give a bit of information on that. So F and G are pure unit quaternions. that means composed of the units I, j, k, and so they are pure unit quaternions squared to -1. You can take any general quaternion x and split it in this way: x plus minus fxg times 1/2, and that's very nice to work with when you split signals in when you use a conventional, what you could call nowadays already conventional two-sided quaternion Fourier transform. And now, if you take this algebra here for special relativity, which has the opposite signature of, I guess, the one that Garrett used, but in this algebra you have a sub-algebra of, which is sum of the quaternions. It's composed of the E0 of the time vector squares to -1. Oh, sorry, it should have the opposite signature. I'm very sorry. You should have here CL3, 1. So please bear with me. Then E0 squares to -1, and I3 in the opposite signature, E1, E2, E3 is a space pseudoscalar, also squares to -1, and the product of the two also squares to -1, and all three intercommute. So that makes a set of quaternion units. And then I3 is dual in this full algebra, having signature CL3, 1 of the time vector. And then you can do the split as well for all the multivectors in this algebra CL3, 1. And it corresponds to the space-time split. And it will split you every signal into two multivector wave packets, one going to the left, one going to the right. And it comes from very elementary structures in quaternion algebra. So, but I won't say more about that now. Okay, now let's go next slide. Now about quaternions, you have the units here and how they are related. You express every quaternion with 4 real coefficients. This is a conjugate. Then you can define the norm. And the inverse is given here. Then we have a symmetric scalar part. So the scalar part is simply a scalar coefficient. And if you take the product of two quaternions and then take the scalar part, it doesn't matter how you order them, or if you take the product of the two conjugates. And the scalar part of the product of three quaternions has a cyclic symmetry as well. Now, every quaternion can be split into its norm times cosine alpha plus a pure unit quaternion sine alpha, and then expressed because A hat, this part here squares to -1 in this polar form or exponential form. And so cosine alpha is simply the real part divided by the norm of the quaternion and the angle between 0 and pi. Now we can define a scalar product by taking the scalar part of the quaternion conjugate of a quaternion times another quaternion y, and it just gives us a conventional scalar product of two vectors in 4-dimensional space. And with this in mind, we call two quaternions to be orthogonal if this scalar product is 0. And yeah, pure quaternions have 0 scalar part, and normed pure quaternion Q is simply squared to -1. Now the quaternion multiplication and determinant, you can express every component of the result of the product of two quaternions with a matrix vector multiplication. You plug in here in the matrix 4 components of the quaternion P, here the 4 quaternions of quaternion Q. And then the determinant of this matrix is simply the norm of P to the power of 4. And this allows us, oh, this is in the way here. I don't know where to put that, maybe up here. So if you multiply quaternion X with a constant A, then you get a new quaternion Z. And that is simply, if you take this definition of a volume element in R4, with this multiplication, you get the norm of A to the power 4 and the original volume element here. and the inverse here. Now we can introduce these derivative operators, and the Dirac operator is simply the vector part of these, and we can also introduce a directional derivative. And if the scalar component of the constant quaternion A is 0, we can replace the partial, the del operators with Dirac operator. Okay. Now, the first substantial thing about the quaternion domain Fourier transform, we have the signal, and the signal has its arguments from quaternions and its values also in quaternions. Then you multiply it with this kernel factor, and the kernel factor has e to the power of minus I, where I is any constant pure quaternion squaring to -1, and then x dot omega is a scalar product of the quaternion for the position and the quaternion for the frequency. So these are both 4-dimensional. Then it's easy to formulate the inverse, a quaternion multiple of the function argument and how that looks like after the transform. And then there's also a, for this transform, a Rayleigh possible energy theorem. So energy doesn't change if you use this transformation. And there is also a formula for transforming partial derivatives and many other nice properties. Okay, now about the spatial width and how it is defined. So here is the effective spatial width of a signal in L2 with unit norm in the direction of a unit quaternion, constant unit quaternion V. And that is the way how you compute it. And here's the effective spatial width not related to any particular direction. That's how you compute it given here. So the direction I indicate with this small index V here. Now, before coming to the uncertainty principle, I illustrated with this speed ticket for Heisenberg. So Professor Heisenberg says, a policeman, you were caught driving 100 miles per hour. And Heisenberg answers, I don't know where I am. Okay. Now, the uncertainty principle for the Qdft is that simply the effective spatial width in the direction of a constant unit quaternion V in position space times the effective spectral width of the frequency in the direction of another unit quaternion in the frequency space is greater or equal the inner product of the two directions divided by 2. And for a unit norm signal, the effective spatial width times effective spectral width is simply greater or equal 1, and that is then direction independent. And this principle here expresses that space-time positions, that is the variance in direction of V, and space-time frequency, the moment variance in the direction of W, they are limited if you interpret these R4 coordinates of coordinates for space relativity, for example. Yeah. And now let us make the step from the quaternion domain Fourier transform to the special affine quaternion domain Fourier transform. So for that, we need special affine phase space transformation. And we have this 2x2 matrix with real coefficients A, B, C, D. And then we have this vector, but the entries M and N in the vector, they are themselves quaternions, so they are not just real numbers. And the transformation shall be lossless, area and power preserving. That means it has unit determinant. And with these coefficients, then we can define the kernel factor for our transformation. And so we take this 1 over 2 pi b squared, and then the exponent we have e to the power of I, capital I over 2b, and the I is a unit quaternion in any direction squaring to -1, and then coefficient A times the norm of x squared plus the inner product, or the scalar product of the coefficient m dot x plus coefficient d times norm of omega squared minus 2x plus dm minus bn, and then a scalar product with omega. And it is this kernel which we use in the definition of the special affine Quaternion domain Fourier transform here. So here is a signal. Again, it is a signal with domain of quaternions and range of quaternions, and the kernel just on the previous slide here. And this transform, where the parameters are in the kernel here, A, B, C, D, and the two quaternions M and N, allows special parameter settings. You recover the quaternion domain Fourier transform, or you get a linear canonical transfer generalization of the Qdft, also a generalization to the fractional Fourier transform. Then you get a lens transformation, free space propagation magnification as well. Now, regarding properties, the special affine Quaternion domain Fourier transform can be computed from the Quaternion domain Fourier transform by first multiplying the signal to be transformed by this phase factor here. Then you perform the easier to compute Quaternion domain Fourier transform, but instead of the frequency omega, you evaluate it at omega over b, so it's just scaling. Then you multiply it by another phase factor after the transformation, and by this factor here. So basically it involves scaling here, the computation of the Qdft, and adding these phase factors here. And now some of the properties. It's left linear with respect to any general quaternion coefficients by construction. It's also right linear, but for right linearity, the coefficients for the linear combination, they have to commute with the pure unit quaternion in the exponent of the kernel here. So that's a restriction. And we have that if the limit of the norm of the frequency goes to 0, then also the SA Qdft goes to 0, and it is uniformly continuous over the quaternions. Okay, we can we have a shift property of the SA Qdft, special affine Qdft. So we can compute the SA Qdft of the signal at the shifted frequency omega minus AS, and we have to take into account this S-dependent phase factor. And we can also add a modulation to the signal, e to the power of I scalar product x dot mu. Mu is a constant frequency, and we get it by also evaluating the SA Qdft of the original signal, but at a shifted frequency argument, omega minus b mu. And then we have this mu-dependent phase factor here to be taken into account as well. This is Rayleigh theorem, which can also be proved for the SA Qdft. And no, this is the inverse theorem. So the inverse is quite easy to compute. You just multiply with the quaternion conjugate of the kernel, and then you integrate over the frequency quaternion, and you get back to the original signal here. Down here you have the Rayleigh partial energy theorem. That means even if you apply the SA Qdft to the signal, the L2 norm of the signal is the same, it doesn't change. And this is a formula for evaluating the partial derivatives of the signal. So here is d by dx v, and v in this case is one of the coordinates, the real part or ijk part. You differentiate the signal. You have to add this term here. And then if you take the norm and integrate over position space and multiply with B squared. It's the same like taking the SA Qdft of the sigma, its norm squared, and multiplying with the corresponding frequency component with the same index squared, and then you integrate over the frequency space. Okay, now we come to the uncertainty principle. So the spatial width in one direction times effective spectral width in another direction is norm of B. Then here you have the scalar product over 2. And furthermore, we have as a corollary the direction independent principle here for delta x delta omega is greater or equal to B. And the nice thing here, you can sort of tune the uncertainty by changing this parameter B here. Okay, so that's, I reached the conclusion. And so we basically lift the special affine Fourier transform to a higher dimensional quaternion algebra domain integral transform. It has many applications, and here is the original introduction of the special affine Fourier transforms. Yeah, maybe there's one paper I wanted to show. Here, this is 5 years ago, the definition of the quaternion domain Fourier transforms, which are lifted in this case to special affine Fourier transforms. Yeah, and so that's my last slide. Thanks a lot for your attention. Yeah.
Okay, thank you a lot, Eckhart, and I think we have time for some questions. Is there any questions?
Parece que Bert Schmeichel tiene también la mano levantada.
Okay. Yeah, I don't see it. Who has their hand up?
Le activamos el audio, ¿no?
You can hear me at least?
Yes, I can hear you, Bernd. Yes.
Oh, hello, Eckhart.
Hello.
Hello. Question is, you mentioned the opposite metric. Am I right that the Fourier analysis carried out here is done on a peculiar space of Minkowski spacetime in the opposite Lorentz metric?
Yeah, I can skip back to that slide.
So the main space units, I don't speak now of line elements, but space elements. The main space elements should be a volume, a space-time volume, and a time. Is that true?
Yeah, basically, okay, my mistake, it should be CL3,1, and then E0 is.
Oh yes, we got this. You mentioned this. That's okay.
Yeah,
that's okay. Yeah. We turn it around, 3,1. But is it right? You have then the space-time units, the line elements or space elements. Let me call them space elements. A volume, a unit volume, E1, E2, E3.
Yes.
Space-time volume, which is the
product of the two.
The director.
Yes. Yeah. That is used for computing this duality here.
Okay.
And then this durable split quaternions can be generalized to the whole 16-dimensional algebra.
Right.
And it can process signals in this whole algebra. So fully multi-vector value.
I got this. I got this. So it can immediately be carried to the bivectors. True?
Yeah, to all the bivectors.
Space-like bivectors. And then you can generalize it to the whole space. Yes, okay, yeah, got it.
Right.
Thank you.
Oh, you're welcome.
Okay, other questions? So I'd like to, what are some applications that you mentioned that would be best handled by these Fourier transforms?
Yeah, traditionally, quaternion Fourier transforms were applied in image processing, but then you had only, okay, it was already quite advantageous because you could take a plain image and the domain of the signal was the XY space, so two-dimensional space, but the range was in quaternions, because in quaternions, the IJK components can beautifully express the colors, and it's a non-marginal, it's a holistic expression. But it limited to be applied to signals which have a 2D domain. But now with the quaternion domain Fourier transform, just some 5 years ago, you can really process signals that live as a domain also on quaternions. So mapping quaternions to quaternions. And that's very nice for physics because 4D signals, also as Maxwell formulated his equations already completely in quaternions, that becomes makes the value of this transformation much wider applicable. And now if you introduce this modification or this generalization to the special affine quaternion domain Fourier transforms, then all the other transforms like fraction Fourier transform, linear canonical transform, etc., which some of them I listed, they also become accessible and useful in this wider setting, and in particular, again, I think for physics, then not only limited to physics, any area of technology, engineering, etc.
Thank you very much for this very nice talk. And I suppose we should go right on to the next speaker, which is Juan Boris Reyes and Marco Antonio Perez de la Plosa. Is he here?
Yes, I'm here. Can you see my slides?
Okay, I do see you, and I see your slides. So Juan is going to talk about solutions of inhomogeneous generalized Moisy Fiorescu systems in Euclidean space.
Okay, thank you very much. I want to start thanking the organizers for giving me this opportunity. And in particular, I want to thank Professor Gregoriav Polynomials for his kind invitation to participate in this very nice event. Okay, so today I will talk about how to find solutions for some non-homogeneous or inhomogeneous generalized Moisy Fiorescu systems in Euclidean space. Okay, so this talk is based on this work. It's a joint work with Professor Juan Boris Reyes, and it was published in 2019 in Advances in Applied Clifford Algebras. Okay, so as an introduction, I want to see some background on the problem. If you consider this system of partial differential equations, and you consider the Cauchy-Riemann operator, and you rewrite the system in terms of the function g defined below and the function f defined below, you can simplify the system into this equation that sometimes is called the D-bar equation or the D-bar problem. In here, the operators, the first one, as I mentioned to you, is called the Cauchy-Riemann operator, and it's defined like this. While its conjugate in the right-hand side, we have defined like this. Okay, so if you apply the operators, the previously defined operators to a holomorphic function h, we obtain that the function h, yes, applied to the Cauchy-Riemann operator is equal to 0, and if you apply the conjugate operator, you obtain the derivative. Okay, these two operators are really important because they factorize the Laplace operator in the complex case. But now it's important to introduce the following Borel-Pompeiu formula. if you consider omega a domain bounded by a piecewise smooth Jordan curve, and if you have a function of the class C1, if theta is a point in the domain, then you can rewrite F in the following representation. If you notice in here, this can be seen as a generalization of the Cauchy integral formula, right? So in this case, you have to check that you have, if you define F like H minus this second integral appearing in here, okay, that can be written as H plus the T operator, and writing down theta as psi minus I eta. And in here, H is exactly the Cauchy integral, and T is exactly the Theodorescu operator that satisfies that it's a right inverse of the Cauchy-Riemann operator. If you rewrite F as H plus T, then you have completely a solution to the original problem, the D-bar problem. Okay, so if you notice, it's important to have in our theory very good generalization of the Borel-Pompei formula. This problem is established by several authors, for example, Becqua or Weger or Henrici. You can see this problem solved by using the Theodorescu transform, as we saw in the previous slide. Okay, so next I want to pass and to start writing this problem in a more general setting. This is why I will start with basic aspects of Clifford analysis. I will understand Clifford analysis as a function theory for the first order vector valued Dirac operator in the Euclidean space Rm plus 1 with m greater than or equal to 2, which generalizes in an elegant way the theory of holomorphic functions in the complex plane to higher dimension, and it provides at the same time a refinement of the theory of harmonic functions. So in order to everyone recall this theory, I want you to see that one of the basic properties relied upon in building up this function theory, the Clifford analysis, is the fact that the Dirac operator defined here below factorizes the Laplacian, yes, through this relation. Okay, in here X is an element in Rm plus 1, and by E I denote it's an orthogonal basis that satisfies the following multiplication rules. I want you to recall that Rm plus 1 is, in this case, we will denote like this, the space Rm plus 1 with quadratic form of signature 0m plus 1. So remember that these are the multiplication rules in the universal Clifford algebra constructed over R0m plus 1, and then you have the important factorization. Okay, so next I want you to remember that Rm plus 1 is a real linear associative algebra of dimension 2 to the power m plus 1 with the following standard basis set, this one in here, where you have for A being this set of subindexes that are ordered like this, and we denote E sub A as this product with E sub the empty set, the identity in our Clifford algebra. Now, if you consider omega in Rm plus 1, an open set, and if you have a function from omega to our Clifford algebra of class C1, then F is said to be monogenic if it is a solution of this equation in omega. Okay, so we will need monogenic functions for our theory. In general, in this talk, we will denote like this. If you have as a subspace of the Clifford algebra, then we will define the following three sets, E, M, and H. They denote respectively the spaces of smooth S-value functions, left monogenic functions, and harmonic S-value functions. And clearly, we have this chain of contention. Okay. So the next step is the following. I want you to recall also that the following space now with superindex S of S vectors in our Clifford algebra with S between 0 and n+1 is defined as the span of this type of elements. It happens that if you have the S between 0 and m+1 fixed, this set defined before lead to the following decomposition of the complete Clifford algebra, and we can denote like this the projection operators. Okay. Notice in particular that for S equal to 0, then this space is isomorphic to the real numbers, and for S equal to 1 is isomorphic to the R0 n+1. Okay, now this is why an element in this form that we can represent like this in Rn+1 is therefore usually identified with this type of elements in Rn+1. So if you have x and y two 1 vectors, it's well known that their product xy splits in 2 parts like this. Okay, where the first operation is the scalar part of the product, and the second addend is like this, is the 2 vector or the bivector part of the product, both given by these formulas. Okay, so in general, if you have 1 vector and V and S vector, then you have that their product decomposes also in a similar way as before, but now I want you to notice that the first part is an S-1 vector, and the second part is an S+1 vector. Okay, so we finish with the basics on the Clifford algebras and the notation that we will use in this talk. Okay, so now I want you to introduce what we call the generalized Moisy-Theodorescu systems. So if you have the set of S vectors in our Clifford algebra constructed over the quadratic vector space Rn+1, and now we will consider this triple of natural numbers Rpq with R between 0 and n+1, P between 0 and q, and R plus 2q less than or equal than n+1, and we will define the space Rpq as the following sum. Okay, so for an element in the previously defined set, okay, a smooth function in there defining an open subset omega, which decomposes like this. We have that now with this notation, the equation Dirac operator applied to the function f is equal to 0 is now equivalent to the following system in here that I have a special notation for it. Here the differential operator d plus and d minus act on smooth S vectors, okay, or set elements in this set as follows. It's worth mentioning that the first element is an S+1 valued function, while the second one is an S-1 vector valued function. Okay, so the system in here is called the generalized Moisy-Theodorescu system, And these type of systems were introduced by Professor De Lange. Okay, let's see why we call this the generalized Moisel-Theodorescu system. And I will check some particular cases of this system. First, if you use P equal to 0, Q equal to 1, and R between 0 and N plus 1 are fixed numbers, then the previous system reduces to the so-called Moisel-Theodorescu system in R N plus 1. This system was worked with by Professor Juan Boris Reyes and Professor Richard De Lange in this paper. Another particular case of the system star is when you take P equal to Q and equal to 0, R between 0 and N plus 1, then this system reduces to the generalized system like this, and its solutions are called harmonic multivector fields. So this is another particular case of our general Moisel-Theodorescu system. So a third particular case will be if R is equal to 0, P equal to 0, and Q is the greatest integer function applied to N plus 1 over 2, then F is R plus valued, where R plus is the even subalgebra of our Clifford algebra. And in the particular case, R equal to 0, P equal to 0, and N plus 1 equal to 3. Then the original Moisel-Theodorescu system is reobtained. If you rewrite like this, the function F0 and F2, then you have the following system that can be written in the system form like this. This gives rise to the system satisfied by these 4 functions. Okay, this system, for example, was treated by my mentor, Professor Shapiro, in this paper in 1997. Okay, so another particular case, and maybe the last one, if R is equal to 0, P equal to 0, and N plus 1 is equal to 4, then Q is equal to 2, and put for given values smooth functions Fi like this. Then for a function defined like this, smooth function, you obtain the following system that can be written like this. Both equations give rise to the same system to be satisfied by F defined like this. And this is the very well-known Fourier system in R4 for so-called left regular functions of quaternion variable, and it lies at the basis of quaternion analysis or quaternionic analysis. So by these particular cases, I have shown to you that our system, the system star, can be seen as a very good generalization of the Moisel-Theodorescu system. Okay, so this last system was introduced by Fourier itself. Okay, so another particular case is when you have these choices of the natural numbers, and then F is in R minus, where R minus is the odd subalgebra of the Clifford algebra. Now I want you to introduce the non-homogeneous or inhomogeneous Dirac equation. This is the fundamental tools in order to solve the following non-homogeneous problem that, as I mentioned to you at the beginning, it is called the D-bar problem. Remember, is the Borel-Pompeiu integral formula. So we want to introduce a nice generalization of this formula for our setting. Okay, so the first important thing is that an important example of a function which is both at the same time right and left monogenic is the fundamental solution of the Dirac operator, and is given by this formula, where A is the area of the sphere in Rm plus 1, and this is the fundamental solution of the Dirac operator, as I mentioned to you. Okay, so it will play the role in Clifford analysis as the Cauchy kernel for complex analysis. This is why we called this the Cauchy kernel in our theory. Now, for bounded functions of class C0. The Theodorescu transform is defined by the first integral appearing in here. And also, we can define the Cauchy type operator defined like this. Here, N denotes the outward pointing unit normal to the boundary gamma at Y in gamma. Okay, so which properties are important for us? They are established in the following lemma. If you have a function in this intersection of classes, then we have, if you notice in part 1, we have the analog of the Borel-Pompeiu formula for our theory. The second property, if you remember well, is that this version of the Theodorescu operator is also a right inverse of the Dirac transform. And also that the Cauchy integral defined before also is a monogenic function for our theory. Okay, now as we have the analog of the Borel-Pompeiu formula, you remember that it solves immediately the inhomogeneous or the non-homogeneous Dirac equation or the D-bar problem established before. And the solution is given like this: the Theodorescu operator applied to G plus a function H, where H is a general monogenic function. Okay, so now it's important for us to introduce the main result. And in order to do that, we have first the following definition. If you have F1, remember, in the set of harmonic functions, put values in this previously defined set, we will say that an F2 function defined like this, also harmonic in this with values in this set, is called an hyperconjugate harmonic to F1 if the sum of F1 and F2 is a monogenic function. The pair F1 and F2 is then called a pair of hyperconjugate harmonic functions. And remember that there exist several generalizations of conjugate harmonic pairs. We define like this in this new theory. Okay, so the main result is the following. We want to solve the following system. If you have a function G, a function of the class in here, then the inhomogeneous generalized Moisel-Theodorescu system. So remember, this is the non-homogeneous version of the system star, where G is a function in this class, has a solution if and only if for the function P defined like this in below, we have the following requirements. The first one, either is identically 0, okay, or B, it has an hyperconjugate harmonic function. If it is true, then the general solution of the non-homogeneous version of the generalized Moisel-Theodorescu system, then the function that is the solution F is given by A star like this, or in the second case, if you have a hyperconjugate harmonic function, B star, in B star, the function, the solution is given by this formula. Here, H1 tilde is a harmonic hyperconjugate of the function minus P, defined like this. And H1 hat, or hat H1, is an arbitrary monogenic function. So I want you to give the sketch of the proof. The first thing I want you to notice is that, and it's really important in order to understand the solution, is that the system 2 is in fact a restriction of the non-homogeneous version of this equation. Okay, remember that this was the D-bar problem for the Dirac operator. It's a restriction when you take a function like this and with a function like this. So if you rewrite the restriction for these two type of functions, then if you write down the solution, remember that once we have the version of the Borel-Pompei formula, you can construct the solution like this. Then you can write down in terms of the components, the system, or the solution, the solution like this. In here, the couple H1, H2 is a hyperconjugate harmonic pair. H1 is defined like this and H2 defined like this. And you can say that if P is already the zero function, then had H1 becomes also the zero function, and both the necessity of part A, okay, and the formula A star is proved. Okay, if in the case P is not identically zero, then you can define H2 like this, meaning the existence of the hyperconjugate harmonic function to this function that, remember, is minus P, which whenever it exists will be denoted by tilde H1. Thus, the necessity of B is also proved together with the solution B. And in order to prove the sufficient part, the only thing you have to do is reverse the reasoning. Indeed, A is true. If A is true, then one can take H2 as the zero function, implying each one to be an arbitrary monogenic function. Okay, and then you have the first formula, no? If part B is true, then you can take in this equation the function H2 to be minus P, and hence H1 can be taken as H1 hat plus H1 tilde for an arbitrary monogenic H1 hat. And thus we have the solution and the theorem is proved. So I want to finish my talk by saying that our approach provides very good, I think, generalization and certain consolidation of the hypercomplex method concerning the solvability of the D-bar problem in the spaces of functions, satisfying different systems in the framework of Clifford analysis and in particular in quaternionic analysis. So thank you very much. And if you have any question, please do it.
Okay, thank you very much, Marco. Very interesting talk.
Thank you.
I'd like to just say one thing. I wonder if you heard my talk, whether you think there's any possibility that Clifford analysis and geometric analysis can be unified by the way I suggested. Well, we can talk about it some other time, but I think we could maybe make some progress on that.
Yes, I believe that maybe you are correct, and we can talk about it later.
Are there any other questions? Okay, in that case, I guess we should probably go on to the next speaker, which will be, thank you very much, Marco, and I'll be in touch with you about these other ideas. And so the next speaker will be Pablo Enrique Moreira. Is he here?
Yes, I'm here.
Okay. Okay, very good. Okay, so you'll be speaking about complete systems of time harmonic Maxwell equations for high-roll media. And it's with Vladislav Kopchenko and Michael Porter. So it's good to hear from you again. So go ahead, you have the floor.
Thanks. This talk is called Complete System of Time Harmonic Maxwell Equation for Chiral Media. This was a part of my thesis. This is a joint work with Dr. Vladislav Kopchenko and Michael Porter. This is the outline. But first, consider the Maxwell equation in no-chiral inhomogeneous medium, which has the following form. So these are very difficult equations. So Dr. Vladislav Kravchenko in this book, Applied Quaternionic Analysis, shows that these equations can be reduced if we use these notations. The original system can be described or is equivalent in sortless condition, is equivalent to the following quaternionic system. So here are the Mosil-Teodorescu operator. M is the multiplication of on the right. So we are interested in how to solve this part. So we are able to solve the original Maxwell equation. So remember, these equations are equivalent to solve under certain conditions these DM solution. So we are going to work with the complex quaternions. Here, Q is this in Q0 plus Q1, E1, Q2, E2, Q3, E3. But here, these Qs are complex. The units satisfy that the square is equal to -1. The same thing of the real quaternions. The only thing that I need is the complex unity commutes with the complex, with the quaternionic unities. The important thing, a big difference between complex quaternions and real quaternions is that here in complex quaternions exist zero divisors. So we are going to work with two special, in this case, this complex quaternion. Here we write Q as Q0 plus the vectorial part Q. They are the definition, is the usual. Q, the scalar part is this part, and the vectorial part is the rest of the Q. So we are going to work with these special numbers. And remember that M is the multiplication acting on the right. So we have these identities. So we're going to work also with the Mosil-Teodorescu operator, which is this, that acts on functions in as follows. So here applies the divergency, the gradient, and the curl. A function is monogenic if and only if this happens. So we are going to work with transmutation operators. So I need this definition. F is called a non-vanishing coefficient if satisfy these three conditions. With the aid of F, we construct these functions, xn and tilde xn, in this way. For certain cases, it's easy to calculate these functions. For example, when f is equal to an exponential, it's easy, very easy to calculate this x and x tilde. And the formal powers associated to the non-vanishing coefficients are defined as these equations. So if you see, is under certain cases, it's easy to calculate xn, tilde x, so it's easy to calculate the formal powers. And the important thing to define this is that exists an invertible Volterra operator in this way with continuous kernel that transform the power of x on or formal powers. So this is a good thing about these operators and satisfy these conditions. So if you see this condition means that if we have if we have an harmonic function, the harmonic function on the image of t, you solve this part of the left side. So this is an important thing. It's easy to calculate these harmonic functions. You transform into another function who satisfies another differential equation. And these operators satisfy this following relation. You can see this the definition of t and how you can if the way that you can write this kernel F, you can see in these articles, the Campos, Karpchenko, and Torba. So the important thing is that if we use these operators, then we can define a quaternionic operator in this way. Tf applied to you is the sum of 4 transmutation operators and satisfy the following thing. The scalar part of Tf is Tf applied to the scalar part of u. The vectorial part of Tf is equal to Tf applied to the vectorial part of u. Tf applied to the sum is the sum of T of f. And in this case, I'm only work on the third variable. Here I need to assume this symmetry of on x3. Since this operator we need minus x to x, so we need this symmetry. We have these properties, and the important thing that the Tf is continuous, since we have Tf is the sum of 4 continuous operators. Also, the Tf, the inverse of Tf, can be shown that can be right in this way. Also, Tf is continuous on the norm L2. And the important thing is this. Remember that our original problem, this problem can be reduced into this problem. So we are interested to find solution to this. And here is the important thing. For you on C1, the following relation holds. So d plus m, here is f over f, E3. Applied to Tf is equal to T1 over f applied to du. So monogenic functions can be transformed into solution of d plus m. Since these operators are invertible, we have the following situation. If u belongs to the kernel, that means that u can be transformed into solution of D plus M. And this is the thing that we want, transform functions that we know. This function U can be approximated by polynomials. And since we have how acts TF into the polynomials, it's easy to check how TF can be seen. So here is the proof. Is only check these steps. It's very easy. And a system of vectors are cal complete if satisfy this. And since we know how acts TF over polynomials, remember that TF applied to the power of x is phi n. So we need only to find a complete system. In this case, we are interested with lambda is 0. In our work, Dr. Klavchenko and Michael Porte, we find a complete system here in the kernel of lambda m plus m. So in this case, take lambda equal to 0. So the polynomials that we use are the I called Gregoriav polynomials. The Gregoriav polynomials are defined by recurrence in this way. And remember that TF applied to x3 is equal to phi1, and phi1 is very easy to calculate. So we only need transform these Gregorian polynomials to obtain a complete system of solution of the Maxwell equations. This theorem can be seen in this paper, regular quaternionic polynomials and their properties. So the system is complete in D for a ball. Then a monogenic can be right in this way, and the coefficients can be calculated also in this way. So since this system is complete and our quaternionic operator TF is continuous, this complete system can be, this system TF applied to this system is also complete. Also, if we have this, we have subset in a frontier, then also is complete in L2. This can be seen in this paper. I define the operator only in the variable x3. In the similar way, this operator can be seen acting in these three variables. So we define let f j a non-vanishing coefficient in the direction x j, and if we write f in this way, that means f is separable. We then know the composition of three operators in this way, and also we have the following corollary that is easy to check. So this composition of three of these operators, if we compose three of these operators, we have the same idea, dm to apply to d f over f. We have that if we have a monogenic function, we transform monogenic function under the TF, a solution under the D plus M. Remember that we want only vectorial solutions. Here we only want vectorial solution. So we need, since this operator transform vectorial functions into vectorial functions, we need to find a way to transform monogenic functions on monogenic function without a scalar part. So it's known that this operator transform monogenic functions into monogenic function with start equal to 0. So we have this important operator. So in this case, if we have a monogenic function, you transform under F to monogenic function without the scalar part, and then apply TF to this new function, and you have a solution of T plus M TF over F. So you can recover the function H and E who satisfies the Maxwell equations. So if we define this TF applied to the Gregoriav polynomials, we have the following result. Every function in a ball can be expanded into Taylor series in this way. The proof is very easy, since if we have a function in the kernel of D, since TF is invertible, is monogenic, and the monogenic function can be written into Taylor series with polynomial Gregoriav. So we need only to apply TF here, and the result is done. So if we have separable functions, solutions of the, we need epsilon and mu separable functions. All the solution of the original problem can be obtained in this way. The important thing that mu and epsilon need to be separable, and this function u and b are monogenic, vectorial monogenic functions. And due to the Rayleigh theorem, we have the following. If we take epsilon and mu as before, every solution of Maxwell equation can be approximated set under the image of Gregoriav polynomials. Since the Gregoriav polynomials are in monogenic function, if you apply a continuous function, these also are the image of complete system also is complete. So here we prove that that any function who satisfies the Maxwell equation can be approximated in this way. In this special case, that in the inhomogeneous chiral media. So this approximation of using quaternion analysis also can be seen in this problem. The Maxwell equation of tiny harmonic electromagnetic fields with these constitutive relations. If you consider these functions satisfy the following equation: D plus a constant, D minus a constant. These are vectorial equal to 0. Here, alpha 1 and alpha 2 are these. And if we have row 1 and row 2 in this way, the vectors E and H can be recovered in this form. And an important thing is that any function here, for example, if gamma is 0, this operator T plus lambda can be seen as a direct sum of 2 of D M here, T plus M, T plus M. So in the similar way, the last problem can be seen and sum of 2 of these problems. So I think that this approximation of problems are very useful. So here, so this problem can be reduced into a 2 of D plus M. So this is all. If you have any question.
Are there any questions? I think exact solutions are very difficult to find to Maxwell's equation or any other equations, really.
Yes, but in certain cases is can be these functions are very easy to calculate in certain cases. Since we have, for example, when f is equal to an exponential, here are very easy to calculate. The problem here with the transmutation, this is to find this kernel. Kernel is very difficult to find. Dr. Lev Kravchenko, Sergei Torba, and Dr. Michael Porter find a way to approximate it. So this can be approximated very easily. So under certain circumstances, in very specific cases, it's very easy to calculate this. So I need to find very easy cases.
Okay, very good. So are there any other comments or questions? We are a little early. I made a mistake, actually. You should have been speaking after the, I twisted, interchanged two talks, but the next speaker will be Carlos Efrain Quintero Navarez and Delia Cervantes Cabrera on Clifford analysis. And,
yeah.
Yeah, okay.
Okay, hello. Let me show you my. Yeah, okay. So let me go to screen. Yeah, okay. So let's begin. First of all, hello to everyone, and yeah, thank you to everyone who organized this conference, and let's begin. So I'm going to talk about universality for sets of 3-valued Qdft gates, and yeah. So let's first go over this. We have the abstract. Finding universal sets of quantum gates is an important part of development of quantum computation science that has been explored in the past with success. However, there has not been much development in extending the very same theory to a generalization of qubits known as Q registers, or as we will call them here, Qnits. There are quantum units of information analogous of qubits that use any number n in natural numbers of basis states instead of 2 as qubits do. So we will have like a 3-valued qubit or a 4-valued qubit. So first let us do a little introduction to qubits and their gates. So, so a qubit is usually said to be the quantum analog of a classical bit. While a classical bit can have one of two values, 0 and 1, qubit can be in a superposition of two quantum states, 0, get 0 and get 1 in this case. So we will have a qubit state, quantum state, that is a superposition of the 0 and 1 state. We will have alpha and beta be complex numbers such that the sum of their magnitudes squared is equal to 1. In such a way that when it is measured, it collapses to a value with probability alpha squared, well, the magnitude of alpha squared for 0 and the magnitude of beta squared for 1. So yeah, this is like a qubit is. So based on classical qubit states, we have two-dimensional Hilbert space. Here rewarded as h of 2, which is of course isomorphic to the complex plane, to c squared, to two copies of the complex plane. So when one has a system containing a number n of qubits, it is described as the tensor product Hilbert space of n copies of this one we just mentioned. We will have these n copies of this two-dimensional Hilbert space, and we will have their tensor products, and this will be isomorphic to having to the power of n copies of the complex plane. So this in turn is a 2 to the n dimensional Hilbert space, having 2 to the n dimensions, of course. And now we are going to present qubit gates. This transformation at this the set of transformations that can be done to these qubits are these isometries of their respective Hilbert spaces. These are the, well, the analogs of the analog of the logic gates that they will have for usual bits. So these transformations are known as the n-dimensional unitary group, E of n, we're guarding here. And for the value of n, the dimension of the corresponding Hilbert space. So each of the elements of the unitary group, n-dimensional unitary group, are represented by an matrix with complex entries. And in the context of quantum computing, these transformations are referred to as quantum gates, analogous to classic logic gates. So some examples of qubit gates here will be NOT gate, also known as the X-Pauli matrix. We already used to use the anti-diagonal two-way matrix. And we have the Pauli matrices X, Y, and Z, X is exactly the matrix we just presented. And the other ones are these ones we showed here, which are very important. I'll always use in these unitary group discussions. And then we have this Hadamard gate, which is known for transforming the basis states, 0 and 1, into uniform superpositions of those same states. You consider that it will turn the one vector into, like one basis vector into a superposition, a positive superposition, and then another will be like a negative superposition. But by negative, I mean one has a negative sign, the other one has a positive sign. So now we will talk about quantum circuits. So these gates we just mentioned are often represented with quantum circuits, very similar to those of classical logic. For example, the X gate is represented as just a line that represents like the flow of information, like there that each line represents a qubit, and we have like this square with an X, which represents that X is being applied on the qubit. So here is the same thing as I said. So for example, if we wanted to apply a composition of two gates, one gate after the other, well, we just have like this, the flow of information will then find the X gate and then the Y gate and then continue. So now let's see, not that we have seen that, let's see what a 2-qubit gate is. So these gates we have presented are active on just 1 qubit each. never doing anything to 2 qubits at the same time. So we can have gates in unitary group of 2 squared, which instead of 2, like it is like the unitary group for 4 that represents the transformations on a 2 qubit space, tensor product of 2 Hilbert spaces of dimension 2 each. And an example of these gates is the CNET gate, which in matrix forming right here as this here. Yeah, so it's right this matrix right here, and in circuit we represented it as we show here. There are 2 wires here, each representing a qubit, and we take the CNET gate will be like this cross right here, circle cross circle right here, and this dot here. So let's see what this does. So are 2 wires for each qubit, and the gate acts only on the first qubit, the one represented by the bottom wire. And it does so depending on the value of the second one, which is called the control qubit. So the one with a black dot there is like it doesn't do anything to that qubit, but it does something to the bottom one, which is the one with the cross. This concept can be extended to an arbitrary number of control qubits. For example, consider the following circuit with 2 of those. We will have 3 qubits in total, and the first 2 ones, the two upper ones, will not the gate will not do anything to them. They will just be like used for telling what will be done on the 3rd qubit right there. Matrix corresponding representation corresponding to this qubit gate will be this very big matrix, because it's in the unitary group of dimension 2 to the power of 3, because there are 2, because there is a qubit with 2 states, and to the power of 3 because there are 2 qubits. So it's the unitary group of dimension 8. So it's an 8 by 8 matrix. These kind of gates are called the Foley gates. It has to act on the target qubits, which is the bottom one, and they do differently according to the value of the control qubit. So the idea of having a control qubit dictate what we done to another one can be generalized as follows. Take the unitary, a matrix U, operator U in the unitary group of 2, which is a 1 qubit gate with a matrix representation given here by here, where U0, 0, like all the entries are complex numbers. So define lambda 1 of U to be this 2 qubit gate in the unitary group of dimension 4 with a matrix representation given by this matrix here. So it will this gates, what this gate does is that if the value of the first qubit, the uppermost one, is if it is the 1, it applies the gate U to the second one, the target qubit. So have the property of taking these 2 qubit states. We notice that we got here the second qubit with a state psi 2 and the first qubit with a state we extended the states of the qubit like this. So we transform it into alpha of 0. So we transform it into a superposition of 2 of the state of what will happen if we don't do anything to the target qubit, and what will happen if you apply U on the target qubit, and they will have like the same coefficients. So this means that lambda 1 of U applies U to the part of the superposition whose first qubit is 1, and otherwise it applies to the entity I2, so it does nothing to the other one. So we call that first qubit the control qubit, and the other one is the target qubit. So our way to write this representation of lambda 1 of u is using matrix blocks inside another matrix. So by this we mean as follows. Considering I2 to be 2 by 2 unitary matrix, and 0 to the 2 by 2 zero matrix we have here. So it looks like here like a 2 by 2 matrix, but each of these symbols is a 2 by 2 matrix. So this will be like a 4 by 4 matrix actually. So it allows us to define an n-qubit control gate as follows. Again, let U be a unitary matrix of dimension 2. That means a 1 qubit gate. And then let lambda n of U be part of the unitary group of dimension 2 to Tn plus 1. That means it's for n plus 1 qubits. And this should be like this, should have this matrix representation right here. So remember that each of these blocks is 2 by 2. So if there are n one of these, then there are well, 2 to Tn plus 1 of these, right? So, and the thing here is that it does nothing to the target qubit unless all of the other ones have the 1 value. So what this operator does is that it checks where the first n qubits have RL1, and if they are, it applies U onto the target qubit. And otherwise, it does nothing to it does nothing to anything. So, for example, we have the lambda 2 of U is big matrix here, which is of course of dimension 8. Yeah, no, it's of the yeah. So it's of dimension 2 to 3. So note that lambda 0 of U is equal to U, just the original matrix. So with this notation, the control quantum gates mentioned before, seen as the Foley gates, can be respectively written as lambda 1 of x and lambda m of x, because the last block of each of these was the anti-diagonal matrix, the X matrix, the NOT matrix. This TC NOT gate is actually short for controlled NOT. And of course, you have exists this anti-diagonal matrix. And now I'm going to present this new concept of, or arrest this new notation I have here of subspace rotations. For this, take matrix U into unitary group of dimension 2, that is a 1 qubit gate with entries defined as before, and consider the unitary group of dimension n for any n in the natural numbers. So we're going to embed U into this last space. We are going to take a matrix from the unitary group of dimension 2 and embed it into the unitary group. We can do this in various forms. For instance, consider this right here. We have an n by n matrix whose first block is has the property of having the entries of U. So is applied into a quantum state, all entries untouched, etc. zeroed until 1, which will be transformed by U. So we can also write this idea of only certain entries as follows. We have here this matrix. We have Tn of PQ of U, and this represents like the all of the entries, and here we give the entries, right? So if I is not in PQ or J is not in PQ, so we must have like entries in PQ in one of these two values. Then it will be the same as the identity, this delta Kronecker we have here, which is of course 0 when ij are different and 1 when I and j are the same. So if I, j are p, so we have TPP. The value of the entry will be U00. We have TPQ, like another entry of the matrix in square, like this subscore we have here. We have U01, U10. We have the other like entry of the square in the matrix, and U11 if one is in the other corner. So this operator will leave all entries in a state vector untouched except for the p and the q, which will have U applied to them. So this happens because these operators have exactly the same components as the identity matrix, except for the ones that affect P and Q. So the operators do a complex rotation. Complex rotation on the two-dimensional subspace generated by P and Q, like the basis states P and Q. So where you can also use an operator B in the unitary group of dimension 3 with a matrix representation as shown here, just 2x3 matrix. So, and all the entries are in the complex numbers and define the following. As we see here is just having again the identity matrix and just doing a different replacement in the corners of a square. And this effectively creates an operator that leaves all entries of the state vectors touched, except for the p and the q and r entries to which it applies b. So then this again does a complex rotation to a three-dimensional subspace generated by p, q, and r. That's why it's called subspace rotation. So we can define analogous transformations for any element of an unitary group for an of dimension n, little n, embedded into another unitary group of dimension big N. So as long as little n is less, it's less than big N, and they are both in the natural numbers. So we call this subspace rotation, and they are as follows. Let us have the unitary group of a big N, lower of an upper cap N. We consider a little n that is less than the other n. So consider the unitary matrix in the but of dimension n by n. So a unitary transformation of dimension little n, and define this thing right here. This subspace rotation, which we represent by a t, and the dimension of the dimension of this space in which it is embedded. In this case, the large space is n, is of dimension big N, and we have P1 until Pn that they must be numbers, natural numbers from 0 to n to the big N, and must be such that they are all different. So for an example, aj in the natural numbers. So this thing right here replaces the relevant entries in the identity matrix, and when it does that, it does the same complex rotation given by this matrix here, this matrix U, but it does it on the subspace generated by P1 to Pn. So it leaves everything else unchanged as defined on the other equations we gave. So still basically choose a subspace. I want to imagine like a three-dimensional space, and a subspace, for example, will be a plane. So it takes a transformation that can be done on a subspace and does it there. And this P1 to Pn represents which subspace is being done onto. So as a side note, when it is understood from the context in which big space we are, it is a unitary group of a big N, we're going to omit the big N. So we're just going to write the T and the entries or the entries on which the operator is working. So notice that as we defined control gates before, as just having an identity matrix with a different block at the end, we can just write them as subspace rotation. So with n being the dimension of the having n+1 qubits. So this is to say control gates are subspace rotations. It can be seen as we have that this subspace rotation given here is this matrix here, which is exactly how we define the lambda, well, the controlled EU gate for n qubits. So we use these definitions and properties in the following discussion of universality. So let's present what we mean by universality for qubit gates. Generally, a set of qubit gates S, including a set of a single gate, is said to be universal if one can build any other gate for any number of qubits only with instances of the elements of that set. What it means is we have a set of gates and we say it is universal if and only if we can make any other gate but with elements from it. So a way of saying this is that a set S of quantum gates is universal if their composition can generate any gate in the unitary group of dimension 2 to the n for any n in the natural numbers. So this valid as the set of gates of qubits is the set of unitary transformations on the state space of the two-dimensional Hilbert space, having n copies of it and then having the tensor product. So we have universality for qubit gates. This notion of universality can sometimes be too strict for the purposes of experimental realization of arbitrary gate. We don't, because oftentimes one is not interested in effectively using a precise quantum gate, but an approximation of it. Like in order to make the exact precise quantum gate, we will need like a lot of gates. But in order to approximate it, we will need a significantly smaller number of those. So there has been development into finding sets of gates that can approximate any gate to a certain degree with a suitable number of instances of gates from the set. So a prominent example of such a set with approximate universality is Boykin's universal set. We have it here. It's the Hadamard gate and this seed gate we presented earlier, but to the power of 4, the fourth root of that operator, and this C0 gate, the control X gate. So it's just like 3 gates. And let's see now how to prove that such a set is indeed universal. Proving that this set is universal is not a trivial matter. So on his article, Boykin cites an elementary universality proof mentioned by this Barenko et al. Article. We can show the citations later. So this in turn facilitates the intuition of how any gate could in principle be formed by this set. The proof will be shown in the following discussion. So let's show an elementary universality proof. As we said, Barenko et al. In their 1995 paper present a proof of a very useful property for proving that certain sets of gates are universal. First, they consider specifically this big set of the C0 gate and the gates from the special unitary group of dimension 2. So these are all 1 qubit gates, but they are special. They conserve orientation. And we have the C0 gate, this 2 qubit gate. That is the C0 gate. And show that the set is universal, as we say next. So in order to do this, first consider an arbitrary gate U in the 2 to the n dimensional unitary group for some n in the natural numbers, an n qubit gate, for example. Mentioned by Rayleigh 1994 paper, we can always decompose these gates into several two-dimensional subspace rotations and achieve D as follows, phase shift. So we have this big here that says you can always decompose one gate, one 2 to the n gate, into these subspace rotations that they are only two-dimensional subspace rotations. So what it means that we use these are all subspace rotations that only have 4 entries different from the identity matrix. And we have here this D matrix, which is phase shift that can be done trivially, very easily using SU2. So if we could construct any subspace rotation, we could be able to build any other qubit gate. So so what this means that we just need to find now how to build any subspace rotation, a two-dimensional subspace rotation. So we're going to do that with the subspace rotation. So consider an arbitrary dimensional subspace rotation for some unitary matrix Uij, which is in the two-dimensional unitary group, and we have Ij are natural numbers larger than or equal to 0 and less than 2 to the n. So write I and j in binary, resulting in two n-bit strings. Take, for example, n equals 4, I equals 23, and j equals 4. And we get numbers in binary. We have this right here, 11 and 4, for example. So consider the gray code sequence for these two strings. This gray code sequence is just like going from one bit string to the other just by doing some one change at a time. So we will have this 10, 11 here, then 10, 10. We change this one, then change this second one, then and so on, right? So this sequence will give us a way to transform the first string into the second, doing only one bit flip at a time. So now assume that we can generate any control gate using gates from S. We shall prove this later. And remember that any control gate is a two-dimensional subspace rotation. So, for example, we see that this control gate right here is this over here. So, however, this only allows us to do rotations on the control gates. Only allows to do rotations of the 2 bits. On the subspace of the last 2 entries of the vectors of the states. So this gives the idea of trying to find a way to change the entries in which the control gate acts. So for this, we will use the Toffoli gates as follows. For the 4-bit case we presented earlier, look at this one here. So 4-qubit gate represented in the circle above checks where the first 3 qubits are 1. And only then does it apply the NOT or X gate to the last qubit. So this does a very nice thing of having a checking property. It only affects 2 base states whose first 3 qubits are all 1s. And we can take advantage of this checking property to create a gate that affects any other 2-dimensional subspace. So here, this right here is a subspace rotation, but it has some really specific rules. But we got to change which element, which subspaces is affecting.
Okay,
so
you have 5
this is done as
minutes.
follows. Oh yeah. So this is done as follows. Using an example, the first 2 strings, 10, 11, and 10, 10 of the gray code sequence presented before. So here, this gate here, instead of checking that the first 3 qubits are all 1s, it first changes the second one. So it now checks that the second qubit is actually 0, which is the first 3 ones we have here. So this is what you said, and at the end, this turns this 10, 11 string into 10, 10. So it does the first step of the gray code we showed before, and we have the other steps of the gray code right here, and yeah, they are done with these gates. So we end up with this having changed I to this 1111 string and j to this 0111 string, and the good thing here is that they know only different one qubit, so they can be operated with just a control gate. So in order to do all these changes, we just compose all those gates we showed before and get this whole thing, and we call this gate G. So our final result is that also we can compose the gates in the opposite direction, and we get the inverse of that. In order to first we do some permutations to the subspace we are affecting, and then we apply what we need to apply, and then undo those permutations. So this gate ends up like this. So this is how we build any subspace rotation. So proved by Barenko-Tao, we can build any subspace rotation as long as we have any outer control gate. So as proved by Barenko-Tao, we can build control gates in this construction right here that use these three ABC matrices that have this property right here, shown here in question 17 and 18.
Sorry, you have 2 minutes left.
So, okay, wrapping up. Is the qubit, it's the qubit way of showing universality, doing some notations and other things, and using control gates. So, the result here is that the new thing right here is that we can do this also with these so-called Q-trees. These Q-trees are analogs of qubits that use three valued qubits that instead of only being 0 and 1 are 0, 1, and 2, and are represented by a state like this. So the thing right here is that we present this transposition gate, this trans gate, and present this circuit right here, rotation gate, and well, we make a very similar construction, but that instead of acting on qubits, it acts on qubits. 30 gates we showed, and it does also this changing and of the indices, and yet we end up in this 3 other new indices that differ only on one qubit. At the end, we get this other construction with this G gate too that does any subspace rotation. So at the end, we also show how to have any gate, any control gate built with these subspace rotations. And so yeah, that's it. At the end, we show how to it is shown how to build any gate by first decompose any Q-tree gate, but first decomposing into subspace rotations. We show how to build those subspace rotations, and finally we just use that for building the Q-tree gates. So in conclusion, we built some concept of quantum computing and showed that we presented the concept of a Q-tree and Q-tree gates using a similar intuition to the one that was using the discussion of qubits. And finally, we have adapted Barenko's proof for qubit gates, Q-tree gates, and gave a brief discussion on how this could be adapted to arbitrary valued qubits, which were referred to as Qnits. It should allow us to speak more generally about universal sets of gates, as this will no longer limit the use of such sets and formalize the usual qubit states and transformations. So yeah, that's it. I don't know if we have time for questions. But yeah.
Okay. Thank you very much. Are there any questions or comments? I have a comment, but I'll see if somebody else has one first. Yeah, I was a little surprised. I expected to see more Clifford algebra. Of course, you can translate Pauli matrices and so on directly into Clifford algebra. But have you done anything actually translating into Clifford analysis?
Yeah. The thing over here was that, I mean, there is this Boykin proof of universality that actually uses Clifford analysis right here, but for this universality thing. But the truth is, there is some work in doing this, and actually, I have some of that. But at the end, I made some good amount of progress into showing this. Well, into doing this the regular way without the Clifford analysis. However, it would be worth to show that. However, most of the process I had done was without that. So it will do. It will be nice to show that we can use the this so-called space-time algebras to show to do the same discussion and see how some calculations are simplified by that.
I guess the title was from another talk.
Yes, that was my mistake. I interchanged the order.
No,
but
yeah, okay.
I would like to mention one reference that I know by Timothy Havel and Chris Dorn. They actually tried to translate some of the language directly into Clifford algebra in a certain way. I don't have the exact reference to the paper, but you can look up Timothy Havel and Chris Dorn. I'm sure it would come up. Maybe I can find it.
There is this Boykin article. Well, no, is this Carlo Cafaro? You mentioned Carlo Cafaro?
Pardon?
Did you say Carlo Cafaro? Sorry, didn't hear.
No, Timothy Havel and Chris Dorn wrote an article.
Oh, okay. No, I didn't know that. But there is this Carlo Cafaro, this Italian. Actually, Dalia showed me that article at the beginning, where it actually does this universality discussion for quantum gates in the context of space-time algebras and Clifford algebras.
Okay, so I'll write you. I'll get you the reference to that and send it to you in an email. So I understand that Professor Yatchik has canceled his participation, so we will have a longer line. But then again, another professor, which was in contact with who I know, might be here, could make a few comments by Shmirko. I got the name, Professor Shmirko.
Oh, yes.
Okay, good.
Thank you, Garrett. I just recall a book of mine that I published in 2014. Name is Decay of Motion, and was published at Nova Science Publishers. And there's a chapter in it it's called Whereabouts of Two Qubits in Minkowski Algebra, which is, so to say, the rigor of this whole qubit story, as was introduced by Kaufmann and Lomonaco. And I calculated it over some 10 or 20 pages. Anyone can try to repeat this calculation. I guess it is entirely bound to Clifford algebra.
Right.
Okay, I don't give answers because I don't even recall my own results. It is a very complex matter, and it is fascinating to go through it.
Well, it sounds very interesting. I've been very interested in seeing that too. So somehow we will get Carlos Quintero's email and.
Yeah, we should exchange a bit. Yes, you're right. We should not ignore each other.
Yeah, that's good. Yeah.
But I must add that Zbigniew Osiewicz certainly would not agree with any of us. This is my feeling. As far as I knew, Zbigniew thought And it would be very interesting to reflect every lecture that we hold here or we have heard here in the mind or in the spirit of Spinev, because Spinev was strongly against the conception of a pre-given rigid coordinate system, whether it be Euclidean, Minkowskian, Clifford, whatever. Spinev just doubted in the possibility to design a rigid space-time and then do calculations with it, because he had the idea that the whole thing was a living process where we should, so to say, calculate in the here and now what goes on in that thing which we called space-time. And here he had this metaphor of the taxi drivers and the triples of taxi drivers and cars. And you need a triple to find out about the velocity of 2 in the triple. And to calculate it all over, the whole space-time story becomes very, very interesting, not only non-commuting, but it is never clear what we get out in the end. If it is a real continuous space or if it is curved, we can make up our mind during calculations. But Spinev was definitely against the idea of an object called space-time. And he always opposed my calculations, and I want to agree with him in the end. He was always right when he said, but Bernd, you make all your calculations in the algebra of Minkowski space. And this is not the space of reality. And the only thing I could say was, you are right, Spinev, but I don't know any other space that we could process in the here and now. It will always be a synchronic picture. In the words of Finkelstein, it would always be a rigid thing. It would never become alive. And this is our real problem, that we have not found out until today what is real, what is matter in reality, and what is space-time in reality. Space-time is as living as all the people in the audience. We are all living, and everything is living, every event. We have no line elements, as Minkowski proposed, but that line element is a living thing, and it is always processed in some kind of processor, and only a few, like Joel Isaacson, knew
Okay, I seem to have...
somebody put the maybe, but it is. I think that this discussion is too much important, and maybe we can continue with that.
Okay. I see that Bill Page would like to make a comment. Also, yes. I'd like to read one quote that was in a letter to Bert Spiegel and me back in 2020. Words from Zbyszko he added at the end of the communication, and he says, nobody can tell you where there is a right road. Could be that everybody is wrong. The only person that can tell you where is the right way is only you, only you. Be yourself. Don't ask other professors. You are own. You are your own best professor. Ask yourself, ask yourself. So that's was Zbyszek's philosophy, so it fits very well with our conversation right now. So
I enjoyed your calculation today. I enjoyed your calculation, but because it was a complete thing and it was done all by yourself. But I could follow because there was compassion and it was living. Thank you very much, Garrett.
Well, thank you. So maybe Bill Page has something. I'd also like to know about his that extra vector that Spishik and Zwischik's work, maybe we could do something with that, where he has a fourth in the quasi group, or what does he call that group? Yeah, it's not a full group, but he has that extra vector and going to the usual Lorentz transformation. Also,
you mean groupoid, I guess.
Groupoid, yes. Yeah, groupoid.
Yes.
So, Bill Page, would you like to say something, Professor Page? Your mic is muted.
Bill,
Yes,
say something.
Yes, thank you. I just wanted to mention that I disagree, and that is the spirit of Spishik. He always started his sentences mostly by "I disagree," and then, but that was actually a compliment, right? That was not a criticism, but a compliment to the speaker. So I disagree in this case that Spishik did not have any idea or any belief in the idea that we have something real. He very strongly promoted the idea that very similar to Alfred North Whitehead, that matter is processed, so that what we mean by matter is in some sense a thing that ages, something on which time passes. And this passage of time is what he insists was adequately represented by what conventional relativity now calls the four vector, but not thought of as a velocity, but thought just as a four vector field that is associated in an absolute way with matter. And he insisted quite strongly that Minkowski had exactly the same view. And so I think he believed that matter was an absolute thing. And also that the relationships between matter, such as velocity, was an absolute thing. So we call it relative velocity, but it's uniquely defined by a system of two bodies. And so it's as much a part of reality as the bodies themselves. And we want to be able to use this notion of relative velocity in a way to describe mechanics. But he was especially disturbed in his analysis of conventional relativity that the notion of relative velocity required three bodies. Because
this is what I'd like to understand that better.
That meant, well, you'd like to understand why that's the case, or what?
Well, actually, I'd like to see how to translate that. What I particularly like is Hessiny's breaking the Dirac algebra, even subalgebra of the Dirac algebra is the algebra of inertial frame. I like that very close connection by splitting, taking the even subalgebra, the Dirac algebra, you get the Pauli algebra, which of course is of an observer.
I think it's easier to see than that, actually. I think that the Lorentz transform is parameterized by a bivector. But the two vectors in the bivector are not the source and the target. The Lorentz
now, he seems to be adding an extra vector in there. I'd like to see where that comes from. But not necessarily going to a groupoid to do it. Might be some way of avoiding the groupoid.
Well, the groupoid comes only from the fact that the transformations he's talking about do not form a group. They because there are multiple identities. There's not a single identity. Right? There's an identity for each object. So each object owns its own rest space. And this rest space is sort of like the identity transformation. But there are multiple rest spaces. And what's known as a groupoid is a category in which there are multiple objects. And every morphism has an inverse.
Okay, I think Jesus Cruz wants to make a comment.
I would like to say a thing. I mean, you know all that, Bill, that Zbigniew formulated motion by beginning with the resting body. Yes, each body, each material arrangement has its own rest. This is one of Zbigniew's famous sayings. And I guess this refers not to total or absolute coordinates, but it refers to reality. What Zbigniew really touches is the philosophy of perception of physical reality. If a body has its own rest in itself, then we have to ask in quantum physics, how does this rest come together? How is it constituted? How is it that the body, that matter, seems to become as stable that we can speak of one definite bunch of matter that is resting relative to itself? This is a process. It's a quantum physical process. And this process is real. It is not just built up by our thought, by our thinking. It is really going on there. And this is where the old classical quantum physics began, with Pascal Jordan, not only with Bohr, but with many physicians who thought about commutative and non-commutative algebras and how they go together, how that can be the mathematical articulation of bodies being in motion or being at rest. What is a resting body? This is a quantum physics question. And I would like us to be aware of this and not just Bindana groupoid. We don't have a groupoid. It's not there. Nobody has ever shown us how a resting piece, how a molecule is constituted and how it is stabilized, because nature is trying to stabilize this little biopolymer all the time. It's restless. Nature is restless, always working out a new stability. So where is that resting piece of matter? And what is it? It is a quantum physics question.
Okay, very nice.
Okay. I then that this is an important discussion, and I think that this was impulsed by the same Zbigniew that was he liked to promote discussion like the way of get advance in the knowledge of nature. Then I think it is the meaning of this discussion. But I think that it is a good moment to stop this here. And I think that we need to either continues this discussion. He liked to say that the scientist is not is subjective, and this is related with this with the idea of reality. And the idea of reality we want to formalize, I think that is going to take to us to idea of groupoid. Then I agree with this idea, but I am sure that we need to continue the discussion, and maybe we can left today this in this point, and continues in another way. Thank you very much for your attention. If you agree, we can stop this for a little break and return to the
some lunch.
4 o'clock in the afternoon. Take lunch, a break for lunch. Yeah. Mm-hmm.
Okay, very good. Brent, did you have a final comment? Okay, I guess his hand is still up.
Wish you the best. Okay.
Okay, so that's fine. So we'll start back at in what 35 minutes.
Okay.
Okay, thank you.
Okay, thank you.
Thank you, Garrett. Thank you, Garrett.
Very nice.
Ok, Pati, no, perfecto.